Thank you for making it upstairs. I know it's like the far end of the building, I guess. So thank you for making the effort. We're here today to talk about chaos engineering. So this is the first talk of two talks, actually just the first talk of two sessions, and tomorrow's talk is going to be tomorrow's demo. So today is not demo, sorry, don't run. Tomorrow will be demo, so that's it's whetting your appetite. We're going to talk about chaos engineering and try to sort out what it means, where we're going with this, and what exactly you could actually learn from it. Quick round, who's done some form of chaos engineering? Who's familiar with the principles and practices? Well, quite a few people. That's good. So my job is done. Thank you. All right. So my name is Sylvain Hellegouarch. Just call me Sylvain if you can. That's probably easier. I'm the ChaosIQ CTO. It's a product company around chaos engineering, and we're more known for the Chaos Toolkit and Chaos Platform products. All right, so that's enough of me. What's interesting is this talk. So it's going to be a talk in 3 acts. The first act will be setting the scene. And then another one will be the characters, the community itself. And the last one, the plan. So I've got half an hour to actually go through those 3 acts, and I'll try to stick to that with enough time for questions. But otherwise, we'll ask questions outside so that if there is another talk after that, they're free to go for it. Right, the one with history. I'm old enough to actually have watched Friends, so that's why I'm starting with that. If you don't know, well, just watch on TV. Look at the past. I guess when I started to actually run this talk, I wondered, should I actually go through the whole history of chaos engineering? But I figured no, purely because Adrian Cockcroft has done a fantastic job at it, and way better than I could. So actually just go and watch that talk at ChaosConf. It's fantastic, and it's well worth it. And it will go and walk you through the whole history of that. I think it's more interesting to go on and watch that talk to actually have me trying to do it again. Nonetheless, we need to set the scene, like I said. So we're going to illustrate that with what we're talking about with case study. And that case study we're going to take is it's a near loss and recovery of America's first space station. I didn't come up with the title, but I'm really proud of using space station in my talk. I've sort of made it. It's a case study made by NASA, because apparently they do those sort of things, space stations. And it's a fantastic resource. You should go on those links on case studies. They're fairly short to read. It doesn't take a long time. And they go well beyond, just space. They come back on Earth and actually do case studies for failures as well. And it's a fantastic read because they tell you what they learned from those things. And that's really extraordinary. Right, so what's the context here? What are we talking about? Well, apparently in the early 70s, the US tried to do their first space station for science, And they decided to launch that after years of design and following fairly, the Apollo program. So why I'm saying that as a context here? What's important here is the years of design and the fact that it was not the first time they did it. Not the space station, it was the first one, but at least, launching stuff into space. Because as we're going to see, it actually played little against them. So what happened here? Well, they suffered the loss of a shield, a sun radiation shield during the launch. Now that's pretty bad because if you put a shield, you expect things to go wrong if you don't have, and heat to go very high very quickly. So losing that wasn't a good thing. Luckily, that was the first launch was unmanned. Otherwise, it would have been fairly bad for them. So, like I said, temperature went high, and the first thing they did was recovery. As engineers, usually that's what you do. If you're on call, you're going to try to recover the system as best as you can first, right? Before doing any learning, anything, you're going to first recover as best as you can the system. They changed the angle of the space station slightly so that the sun radiation would be as strong and the temperature would go down a little. Now, that in itself was obviously quite tricky, but at the same time, they had to keep it in a certain angle so that they could actually still control it. And bear in mind it was like 40 years ago, 45 years ago. No decent computer, no mobile, things like that. It's quite an achievement what they did. And they decided that they still needed to control the temperature. So they had to actually think very quickly out of the box how to do that. And that's what we see those ladies doing on the side. And the next launch was postponed by 10 days. Sometime in software, we take like 6 months if something goes wrong. They decided to do another launch, not the next day, 10 days later. They were crazy. And they managed to succeed. They actually saved the day. So what was the findings? That's going to be a long paragraph here. I'm going to try to go through them quickly. They are excerpts from that case studies itself, so go back and read them. But what's interesting here, like I said earlier, they were, they based off the Apollo program. What they realized is that thing, the shield itself, was not part of the Apollo program. They just added it. But some things like the control management were essentially the same as the Apollo program. So I wouldn't say they were careless or anything like that, but they made assumption about the fact that it worked well and it should work well again. And they didn't realize that adding a new thing was actually a change quite complex in itself, not just a new thing that they added. Well, if we talk about our industry, doesn't ring a bell. Like, I did that in the past, and it's just a small change. Let's push it in production. We've all been there. We've done that. Well, it can have very, very strong consequences. Obviously, you don't do space stations, I guess, most of you, but still, even a small change can have, changes that can have actually dire consequences. Another finding they had was they had years of design, like I said, but they presumed too much. So what they did was the shield was sort of, I wouldn't say glued, but attached to the space station. And when it went up, the pressure and the difficulty of the constraints on the launch actually threw the shield away. And they didn't expect that. So they had lots of design, but it wasn't enough to actually succeed in that case. So they were smart and sharp engineers, probably the best, but they were confused by their confidence in their design, and that provoked the error. And the last finding that I find interesting to us is their design. There are lots of rigor, lots of formalism, lots of documentation. Now, don't get me wrong, do that. Do a lot of peer reviews, documentation, testing, whatever. All those things are perfect. But they realized, damn, it's not enough. We still need to have our intuition as engineers. We can't lose that side of that. We need to realize that as engineers, we have hunch, maybe a bit too strong of a word, but at least experience that tell us, well, maybe we should pay more attention to this or that. And it's very interesting because I realize even though we send space station, we still need that sort of intuition. And what I realize, they really need to have to basically fertilize the whole scientist, field with their experience. They can't just talk to themselves within their team. They really need to go abroad and out of their own team. And it will always be important. That was years and years ago. So it's a different mission, but same take, in my opinion, here. Is on the Mars, and on the rover mission sent to Mars, they realize that you have the cards you want, right? What you try to have as constraints, what you design, what you think, but then you arrive on Mars and then, all bets are off, basically. Things are different. Now, I understand that those are extremely far-fetched, maybe to you, examples, but they relate to our daily, to our domain as well. It's always the same. So basically what they told us is be ready not to be ready, in the sense where keep in mind that things will go somewhere that you don't want them to. We are not mathematicians here. We're not demonstrating through formalism only. The laws of nature actually impact us. And I mean that really. When your hard drive goes down and you lose a volume or something, that's that sort of thing that you don't really expect, But the problem here with what we're going to discuss today about is the impact of that. It's not necessarily that you know that something is going to happen, but what are the consequences of losing this or that? This is what chaos engineering is going to bring you. Fast forward to 2018, we've improved, we are better at it, right? The Insight mission is successful and it's fantastic in my opinion. But as system reliability, especially in our industry, goes, we still have a lot to improve. I'm so sorry it's in French, but when I took the screenshot, I didn't realize I was actually using that later on. But I guess you're familiar with the screen of a certificate that has expired. This one comes from actually a French public service. Now, I know we don't work a lot apparently and things like that in France, but we do tend to be careful about those things. But this one is a minor service somewhere in a chain that nobody really cared for, I guess, and their certificate expired. After 9 days, I just had to use that service, and I couldn't. I wasn't the only one, so I did what everyone does: goes to Twitter and complain. And again, if Twitter is your first alerting system, you don't have alerting system. So try to be before Twitter. That'd be nice. But I didn't complain, I guess. Oh, you can't read that anyway. And luckily, I wasn't the only one, and some people who actually said the same thing, and they have more connection than I do, and they fixed the thing, and it was all good. But sometimes the impacts are stronger. If you were in the UK last week, or if you are a British citizen, you may use the O2 network, mobile network. Well, a similar thing happened. On the infrastructure that Ericsson provides, apparently the first analysis, I wasn't there, but said that a TLS certificate did expire as well. But the ripple effect for that was that the whole mobile network went down for the better of 2 days. But there was no network at all. And it's actually quite stressful because my co-founder and my friend is on that network. I tried to reach him, he was on the road, and I couldn't, so I got worried. Now, luckily it's not, it's not much for us, but imagine if you need to talk to your mother, or she needs to talk to you about, the mess you put everywhere, but, so those sort of urgency, right? So even a small thing that you forgot about will actually impact users in real life. And that's something you want to actually experiment on before they actually hit the problem. A quick tip, if you have TLS certificate and no monitoring at all, just use Google Agenda or something. Set an alarm somewhere saying, oh, in 1 month, by the way, this will expire. Because what happened in the previous example was they bought the certificate 3 or 5 years ago, and they probably just forgot about it, or the person just left. So just leave somewhere some note about it. All right, so we need more reliable systems. And really, truly, I mean that. We do need more reliable systems. I think we need more reliable systems than we need more features these days. That's more critical for our users, that our systems are reliable, because they do trust us to actually provide a feature as service. So it's more important to me that your systems are reliable than there are shiny new features in them. So that's the end of Act 1. We've set the scene. We need reliability. And by reliability, I mean any form of reliability. It can be resiliency, it can be security, it can be, just pick one. It's an umbrella term here. The Act 2, the one with the community. Now, it's important then to note that you're not alone in that. It's not just you. Chaos engineers, SREs, DevOps, sysadmin, basically any engineer should care for that. As developers, we should care for reliability. Any stakeholder in your company should actually care for that. Not just the engineering team. If you can't sell to the rest of your company that reliability is prime, then you are in trouble. So we've created the CNCF working group about a year ago for that. We started to discuss how chaos engineering could help, figure out chaos, reliability. It's a proposal so far. What that means, it's officially not a working group yet. We're working towards that. So I think it's a strong signal that if the CNCF cares for that enough to actually create a working group, that it matters to the cloud native system at large. It's not a little thing. What are the deliverables and the challenges that we wanted to, we had? we had two things, so white paper and landscape. I'm going to start with the white paper. So first and foremost, the white paper, the CNCF is very strong on that. It's not an RFC. It's not a specification. It doesn't tell you what to do. It gives you a good starting point. It's really, a starting point for your journey into chaos engineering. So it will give you solid ground about at least a definition, a set of tools, the use cases, so that you can figure out what it means. I think it's a good starting point. So why chaos engineering? For example, from the white paper, we've got a few use cases I think that would be, yes, that would be the one after. Well, we want to harness improve system reliability. That's the first first one. Chaos engineering is to actually harness your system reliability. It benefits the cloud native system because cloud native has all the properties that will help, that will be quite easy for chaos engineering, during your software development cycles. You'll see that. And it's basically bringing the operational practices into the development world. All right, so some use cases, like obviously trying your network CPU. So for example, trying to increase your CPU suddenly, how your system copes. We know that Kubernetes will manage resources, requests, limits, and stuff like that. But have you tried? Have you pushed your service to the limits? And see how basically they are changed from node to another node. What are the consequences of that change? If your system takes like 1 minute to start, and suddenly it's been moved from machine to machine to machine, but not quickly enough, then maybe you start having a ripple effect that is not very good for your system overall. So it's really a way to actually push your system into places that it doesn't like to be. But you do that in a controlled fashion. You're observing the system at that time. You're controlling the experiment. We'll come back to that. Multi-cloud migration or cloud migration altogether. It's interesting because let's say you want to move to a different cloud or have hybrid cloud. You're not sure where to start, right? But the worst part is you know exactly the challenges you've got on your system. But if you move to a different cloud, yes, it'll probably provide the same features at a high level, but you don't know the consequences from the runtime perspective. Maybe it's slower. What's the impact? And honestly, chaos engineering can be used from the process and human perspective. It's a really socio-technical practice. So it will tell you, for example, let's assume you do a run where you break something, and you say, well, the person in charge usually, we pretend she's on holiday. Maybe you can't even actually reach the machine because she's the only one who knows the password. And for some reason, the wiki hasn't been updated for 6 months. That would be good. So that's the sort of thing that chaos engineering will help you. Very technical, very down to earth. Let's try to prevent, remove all the disk or prevent like simulate a failure in volume. And you've got a stateful application. What happens? How does it impact my data? Right, the second deliverable, and that's we've got those two only. The landscape. You're all aware of the massive landscape of the CNCF. Well, we've got a tiny place for it. Right now, it's fairly not populated enough, in my opinion. We've got those few projects. They all deliver, either fault injections or orchestration around, chaos engineering. But there are so many more. The problem is right now the tooling that you'll find mostly come from some companies who've done some form of reliability testing. But they are very specific to a specific need for that company. So we've got segmented and fragmented tooling space here. So it's going to grow, but it will be some time. So on Kubernetes, we've got quite a few things, but on some other areas, we don't have much. So you'll have to be patient or come with your own tool. That's really the fun bit. Right, so, and difficulty as well. As a tool provider, I may want to actually organize my space in this way. So in the landscape, I'd like to be organized in that place. But we need to think in terms of users. As a user, how do you look for those things? You may look for chaos engineering, but you know better. You don't know where to start, right? You've got many tools, and you're back to square one. Which one should I pick? That's one of the problems of the landscape. It has so many solutions for some specific needs sometimes that you don't know where to start, and it's overwhelming. So we need to decide the right way as a user how to guide you towards the right, right tooling. I think it's important. So the challenge is, it's a new practice, so where to draw the line? Either we go too far, in meaning we start almost becoming like how-to or dogmatic about it, and we don't want that. Or we don't go far enough, and you're probably coming to it and saying, I don't know where to start, it doesn't really help me. And that's tricky, to be honest. As a white paper, it's really tricky to find the right balance. How do we better engage the community? We've got a good community as, in terms of number of people. Maybe you're part of that Slack channel, but it's very quiet. I think people right now are more consumers than, actors on that. So we need to engage. And what we could do is already share your resiliency and reliability stories. The failures, it's fantastic to share, well, this fails for me. Because we're going to discuss about that. And from that, maybe we can start drawing ideas towards what chaos engineering experiments we could actually come up with. So if you, really, if you can, obviously sometimes, sensitive data and stuff, but if you can share your stories, I think it's a very good starting point. Right, so that would be the milestone that our community is facing right now. Complete the white paper. Please come and join and PR and stuff. Find the right way to actually organize the landscape, put more tools in there so that you know where to start, and hopefully submit the working group to the CNCF TOC. So it becomes a true working group. So we need to make a stand, back to what we were saying earlier. We need to make a stand about reliability. I know feature velocity is so big, it's sometimes difficult to fight back against the product teams. But they need to understand that the more reliable we are, the faster we'll be. It's the only way to get there. If we are reliable and we trust in and we are confident in our systems and ourselves, then we can deliver as fast as we can. And that's a community thing on Act 2. Last act is opening up, having an outlook on things. I said the ones here because we're all in this together. It's not just the CNCF working group or just me or a few here and there. We all have a way to actually contribute to the idea of reliability here. So we must not reduce bike shading and stuff like that. We can't reduce chaos engineering to definition and tooling. That would be foolish. Who thinks that chaos engineering is chaos monkey? Right? Well, no, it goes a little beyond that, hopefully. Chaos Monkey is a terrific tool, but it is a tool. It is only a mean. It's one, right? So we need to go beyond those things. It's a deliberate practice. So first of all, it's deliberate. You do it because you decide you're going to do it. It must not be imposed. You're doing it as an experiment. And you want to explore what you don't know. You're using Kubernetes maybe. So many things you don't know. You have no idea how things are going to react. Change a policy somewhere. This morning Liz spoke about the control policies of trying a new thing on trying to implement control policies so that admission policies, for example. That's good. You can test that, see that works, but you really don't know what are the consequences of the system overall. Because if at some point one of your service tries and is denied that, how does it react? What is the ripple effect of that onto the whole overall system? That's the kind of thing, because you don't know, you're going to try that way with chaos engineering. So you're going to build an experiment saying, well, I'm going to try just that, and we'll see what happens. So why chaos engineering? Because reliability is strategic to everyone. I've heard people say that's production system, chaos engineering. It's really strategic to you because, like O2, the O2 network, I'm not sure they did it. They had a good end of week when actually the whole network went down. So it's strategic to your company. It's strategic to your teams to deliver fast and to deliver reliably, and be confident in your own system. So at this stage, I'd like to start opening up a bit. We've said we've got chaos engineering to to run experiments. But at that stage, we need actually to collaborate together. Like I'll say later on, why do you come to a conference? Because you want to discuss with others. You want to see what others do in other companies. You want to collaborate. And that's the only place where you can actually go and talk to your fellow engineers and say, how do you do that? How do you cope with that thing? So that's really, you need a platform. Now, platform is a very wide word here. It's just say we need a space that is neutral where we can exchange and talk and collaborate together. Let's have a short detour before going on. I don't know if you're using Google Cloud, but if you are, they provide very awesome, before Black Friday, they had a long article, extremely good, about getting ready for that, if you were using their platform. They even mentioned disaster recovery and Chaos Monkey, again. But there was nothing actionable. So you got a lot of content, you've got a lot of thoughts, but nothing you can action, nothing you can run yourself. And to me, Google Cloud or any other provider should give you something that you could run against their own platform and say, if you do run this, you will learn those things, right? And that should be actually extremely important. You can't just bet that they tell you, oh, trust us, we've got a good SLA. That's not enough. You want more. You want them to tell you, run this, and if it doesn't work, then you've unearthed something on your platform, on our platform, but on your system. So fantastic place, but next time I hope they'll say, run those experiments as well. So what does it mean, runnable experiments? Like I was saying, why are we going to conferences? It's exactly that. So have you heard of the chaos engineering principles? Yeah, it's a short document basically where folks from Netflix and other places have gathered and basically, stated what it means to do chaos engineering. And they gave us some vocabulary. It's very nice to read. You should actually go and have a look. It's worth the short read. You start with asking a question, right? A question like, what happens if my TLS certificates die or expire? Or what if I've seen that once. This TLS certificate had been renewed, but if I recall well, they had changed the software on the server side where basically it didn't accept some of the TLS, lower protocols. And clients had not been updated. That broke very badly. So once you've done that, you've got your question, you build an experiment. That experiment simply says, I'm going to look for the system when, sorry, I'm going to look at the system, and I'm going to perform one action that will degrade or change the conditions. Some people do breaking, but it's not necessary. What you do is simply change the condition of your system to try to highlight whether or not your first question is actually valid or not. You observe your system. If you don't observe observability, then how can you learn anything? And once you've done, when you've finished, basically you've got findings. Either nothing has changed. That's two things. Either your system is capable of sustaining that specific condition, or you asked the wrong question. So you change something that has nothing to do with that part of the system. And if you found something, then maybe you've found a weakness in your system. And that weakness needs analysis, and that's where you come into play as engineers. So basically, you're doing science here. You're not only engineers, but you become scientists as well. You're performing the chaos, the science method. You ask a question, you form an hypothesis, and you run an experiment, and you find out what gives. It's pretty cool, because you can now say, I'm an engineer and scientist. And you explore your system reliability, your capacity to sustain some failure on some sort. And because chaos engineering is now science, it should be open science. That's where we're coming back. If you do that on your own, you're still not learning from other systems. And that would be so lovely and so powerful if you could just go to a place where you get those findings and those experiments and you run them and you learn from that. You really want other people to actually tell you, oh, you're using SEO. I'm good with SEO. Maybe you run that. Because honestly, I'm not an expert in SEO, so I'd love if some expert could actually give me the basics and just make sure that I'm confident with those things that I've set up. So we must strive to share our experiments and findings. Now I understand that it's not easy because of sensitive data and things like that, but we can find a way to actually share enough that other people will find that valuable. So we need to work obviously on open standards and APIs, so that goes without saying. Kubernetes has paved the way here. Who would have thought that 5 or 6 years ago, so many big players would come together and actually come with one API? And the one thing we need to keep really hard as a community of engineers. That thing is really, really important. If we don't do that again, we'll fail, and we're going to isolate and create silos, company silos on the bricks that we bring on top of that. So we have to be careful there. The World Serverless Working Group is a very good example of that. They're doing a good job at federating across the industry again. And what that leads me to is the Open Chaos Initiative. So we've got the principle. I'm so sorry. We've got the principle. The principles give you a vocabulary that states where we are. The Open Chaos Initiative is more about we need to share that together. We need to work together on that, because if we don't, then we can't learn from each other. So we'll be back, obviously, to conferences, and we'll ask questions. But it'd be nicer if we could go to places and say, can you send me your experiment that you run for that specific use case? And I'm going to run that again. So that's exactly what NISA said on my first example, on the case study that I showed you earlier. We need that. And if those guys were quite smart, I'd say, think that it's important to keep this open, then I think we should learn from them as well. So we need you and your reliability stories. Let's get started there. What are the challenges you're facing? And then how we build chaos engineering experiments, how chaos engineering can help you actually unearth those unknowns. And that's the end of Act 3. But that's the beginning of a movement, I hope. Now, I've put you to sleep, so I don't expect movement right now. But I hope that you'll get enough of this to understand that I didn't want to focus on chaos engineering for the sake of it. Tomorrow, Julian and I will do a demo. Come to the demo, and we'll walk all the way through. But today, I really wanted to actually relate the fact that this goes beyond the tooling. This is really important. This goes across the industry. We need to get better at this, because no one wins when a company goes down because they had a security breach or a reliability issue. No one wins. So we need to get better at it. And that's why we're building Chaos Engineering initiative on that. Thank you very much.